Okay, so my name is Mahbod Majid. Today I'm going to talk about a paper, Efficient Mean Estimation with Pure Differential Procedure Software Squares Exponential Mechanism. This is based on a joint work with Sam Hopkins and Gautam Kamath, who's also my advisor here at Waterloo. So let's begin. The main contribution of our work is a new way to design private and efficient algorithms that we should call the software squares exponential mechanism. Specifically, we apply this method to mean estimation, but we anticipate that this technique would be applicable to many other problems as well. So hopefully by the end of this talk, you should be able to learn about this new technique and be able to apply it to other problems as well. So let's see what is mean estimation, basically, informally. You have some hidden vector mu in RD, and you would take n samples x1 to xn from a distribution D that has mean mu, and your goal is to find some vector that approximates that hidden vector mu, which is the mean. Now, our contribution is that we give the first algorithm for this problem, which is simultaneously computationally efficient. It has of these samples up to logarithmic factors and is pure DP. And as a bonus, we also get robustness and subgaussian rates. Note that any two out of these three properties that we mentioned, it was known how to get any two out of the three, but it wasn't known how to get all of the three at the same time simultaneously. And this is the contribution of our work. So now let's define a private mean estimation more formally. As I said, we take n samples x1 to xn, and we from a distribution with mean mu. The only assumption that we make about D is that it has bounded covariance. Let's say its covariance is bounded above by 1. And for technical reasons, we also assume in this talk that we have access to some estimate of the mean mu0 in a way that mu0 and mu have distance at most of root D. And our goal is to find some estimate mu hat such that mu hat is close to mu with distance alpha, and with successfulity 1 minus beta subject to pure differential privacy. So the question is whether there exists an algorithm for doing this task that requires of these samples and is efficient as in polynomial time in the number of samples at the dimension and is private. So now I'm going to talk about three things. First, I will talk about three algorithms that don't work for this problem or are suboptimal. Then I will try to fix one of them, and at the end I will describe how our algorithm really works. So let's start with three algorithms that don't work. I will now describe three algorithms that don't work, but the thing is that each of these algorithms don't work in a different way. So let's begin. The first one is the Laplace mechanism. This is a fairly simple algorithm. You would just take x1 to xn, you would truncate to a ball of say reduced root D. And then by doing this, you would reduce the sensitivity of the empirical mean of these truncated means. So now you can add Laplace noise, but the thing is, because of this discrepancy between L1 norm and L2 norm, you would end up adding a large amount of noise, and your sample complexity will be off by a factor of d to the half. So this algorithm is going to be efficient, but it's going to have the suboptimal sample complexity, and it's going to be QDP. Another very similar algorithm is just doing the same thing, but instead of adding Laplace noise, adding Gaussian noise. This is going to give us of this sample complexity, but it's going to be concentrated DP, which is qualitatively weaker than pure DP. Now, the third algorithm is using the exponential mechanism. The intuition behind this algorithm is fairly simple. If you have some candidate point that this candidate point is close to the empirical mean of your samples in every direction, then this candidate point is probably close to the true mean. So now, based on this intuition, we can decide whether candidate point, how good a candidate point is in approximating the true mean. So if a candidate point, say the red dot here, for this candidate point, there exists some direction in a way that in that direction, this point is far from the mean of the 1D projections, then this point is probably not going to be a very good point for estimating the true mean. However, if there doesn't exist any direction that's like that, then this candidate point is probably a good point. Based on this intuition, now we can define a score function. This is pretty standard in this is a pretty standard way in designing a score functions for the exponential mechanism. It may seem kind of odd, but it has appeared before. The standard way is to define the score function by how many of the points you need to change to make these points look either good or bad. And in our case, this would mean having one direction, having one bad direction, basically. So, as I said, for the point on the left, for the candidate point on the left, you don't need to change any points to make it look bad. It already there already exists some direction on which this point is far from the empirical mean. But for the point on the right, you would need to change at least some of the samples. You need to move some of the samples to make it look bad. Okay, so now the thing is that we need to, for computing this score function, we need to look at any direction in RD. And the issue is that there is exponentially many directions in RD. So it's not clear how we can really compute this score function. And apart from that, even if we could compute this score function, it's not clear how we can run the exponential mechanism because there are exponentially many points in a ball of, say, radius r in d dimensions. So the sample complex, it can be proven that the sample complexity of this approach is of d up to logarithmic factors, but it's going to require exponential runtime because we don't know how to compute the sample for a single point and how to compute the score for a single point, and we don't know how to sample from an exponentially large set. So as you can see, each of these three methods are flawed in their own way. One has the right sample, one has the wrong sample complexity, one has the right notion of privacy, and one has the one is non-efficient for the exponential time. As you might have already guessed, our work basically gets all of these three d0 deltas at the same time. Okay, now let's see how we can fix the exponential mechanism that I just talked about. Okay, we had two main issues there. First one was that it's not clear how to compute the score function for an exponentially large set, and this comes from a kind of more like abstract problem, whether we can, for which score functions we can do the sampling efficiently. And the other issue is even for a single point, how can we compute the score function? But this has appeared in recent works in efficient robust high-dimensional statistics in recent years. and maybe we can use some of the techniques from there in order to solve our problem. Okay, so let's start with the first one. We have a very abstract problem at hand. We have some score function, and we want to see whether we can sample from this score function, sample from the exponential mechanism corresponding to this score function efficiently or not. Efficiently and privately or not, sorry. And this problem, unfortunately, has been studied before, specifically by Bassi, Smith, and Takuta in 2014, and more recently by Mahbod and Mission in 2021. So basically, if your function, if the score function is both like concave and Lipschitz with respect to the candidates, then there exists an efficient sampler for the exponential mechanism. So now we have some idea on how we can deal with the first issue. We can basically define a concave and Lipschitz function, Lipschitz score function. But let's see how we can deal with the other issue, basically how we can compute the score function for a single candidate. As I mentioned, this has appeared in recent works in robust estimation, in some Gaussian rates for detailed estimation, and privacy by us, and on a concurrent work by Kothari, Manvangas, and Wellinger. In this work, we are going to use the progress made in estimating the mean for heavy-tailed distributions, the work by Lagos and Mandelson, and which was later made efficient by Hopkins. These algorithms, what they do is that they take x1 to xn and samples, they put them in k buckets, each having m samples, x1 to xm, xm1 to x2m, and so on. And then they compute the mean of each of these buckets and name them z1 to z2. Then there is a critical definition here, and we call a point y central for these z1 to zk if y looks like a median for these zi's on any direction, on every direction. Now, a key lemma here is that with high probability, the true mean itself is going to be a central point. And any central point is also close to the true mean. Okay, now that we know a centrality, there is a equivalent definition using quadratic programs, which is using Hopkins and Trapamanderi, Flammarion, and Bartlett. The thing is that the same definition, being a median in every direction, can be expressed as the quadratic program. Basically, we have our bucket of means, we have a contrast mu tilde, and we have a radius of interest r. This radius of interest can be seen as the accuracy of our algorithm. And we have directions v. We want our mu tilde to look like a median on any direction v. And we have VIs, which are the indicators of this. So this quadratic program basically measures what's the worst direction that we can find. What's the worst? What's the worst direction in a way that mu tilde doesn't fall on a good percentile of the projections of CIs. Basically, you would just need to count. This basically counts what's the worst V, such that on that V there are a lot of ZIs that are on that side of mu tilde, basically. Now, if a point has a high quad value, then it's going to not be a good candidate. If it's going to have a low quadratic value, it's going to be a good point. It's probably going to be a central point. So now mu tilde is central only if and only if quadratic program has low value. Okay. Now suppose that you have some point mu tilde that is not central. How can we use this point? So let's say the red dot for the red dot here, there exists some direction such that on that direction this point is not a median of means. Now the thing is, if we take that direction, it is going to take us to the place where the bucketed means the projection of the bucketed means zi's are. And we know that the central points lie somewhere inside those points. So taking this direction is going to take us towards the central point. Therefore, we can use the certificates of non-centrality, i.e. V, to move towards the central point and eventually, and with high probability, to the mean. And the thing is that we don't know how to solve these quadratic programs efficiently, but we know how we can approximate them efficiently. We can use, there is a standard way to solve quadratic programs, and that is through STP relaxations. And this was used in Hopkins and Chapman method to basically solve this quadratic program. And in this work, we also show that in previous works, they use the top eigenvector of the large V. But in this work, we show that just using the V in this, the small V in this semi-definite program also takes us to a central point. Now, we know how to sample for exponentially large set. And now we just realize how we can compute the score function efficiently. So now let's see what's the final algorithm here. We define a score function for candidate point mu tilde, and over the set of directions that we can take as follows. We use the same semi-definite program as before, with the additional constraint that V is equal to Y. Now, the thing is, this program it can be shown that this score function for Y is going to be concave and Lipschitz. And therefore, we can sample from that efficiently and privately. So now let's see how the algorithm works. We have some candidate point mu tilde. We look into, we have to pick one of the directions that we can move into. And how do we select from these directions? We use the exponential mechanism to sample from the STP band function. We sample, we find some direction, we take a step in that direction, and we repeat again until we reach a central point. And this is going to be private because we are using the exponential mechanism to sample from the set of directions. Okay, we do again, repeat until we reach. Okay, so the thing is that our approach is not very specific to this problem of mean estimation. It can be shown that if we have a score function that has all of the properties that we use, a high score function that implies high utility, it has bounded sensitivity, it has Lipschitzness with respect to the candidates, and it has concavity with respect to the candidates. Then we have a large volume of good points basically. Then the exponential mechanism will work. It will give us a high utility point efficiently. And we capture this in a method theorem for SO space score functions that can be seen in our paper. We also use this approach for coarse estimation instead from going to R, radius R to radius root D, but we don't talk about this in this talk. Okay, now here's the overall theorem. You can pause if you want to read it. Now, the thing is that our algorithm is optimal in every term, except for the term mean D log R there, and that is for the coarse estimation step. So our algorithm matches the lower bound on every term except that term. And so an open question is whether we can get rid of that term in the coarse estimation problem or not. Yeah. Now, what's the conclusion? We give the first efficient PDP algorithm of this sample complexity from an estimation, and as a bonus, we also get robustness and sub-Gaussian rates for free. Some directions that to explore are maybe exploring more connections between robustness and privacy, and see and explore where this approach can be applied. Okay, thank you.